guys, and welcome back to this one. Today we are going to be looking at merging two singly linked lists. Subsequently, we'll be looking at merging two lists that are already sorted in normal using normal lists. But this time around, we are going to be using the singly linked list as we've entered into singly linked list as a function, as a chapter rather. Now we have two nodes. The first nodes of two singly linked lists, and what do we do? So basically, we are looking at the brute force for starters, and then subsequently we are going to look at the optimized solution. Now we reinstantiate a value head, and then we call a head at the first list, right? Now with a pointer to the first list, we go ahead to say, okay, while the head is still existing and it's not none, basically we want to append all the values within that list to this value, or the data within that list to this value list, and that's what this while loop does. This one as well. Now we can agree that for every while loop that runs here, it goes through the entire list. So let's say the first list is n and the second list is m. We could take it that the time complexity will be O of n plus m quite easily. Now we have using the Python sort, which is an O of n plus 1, which is an O of n plus m rather, and the log m plus n, right? And that's what we have for this sort. That what basically it tries to do for us is to get those two lists together and sort them according to get those the full list, which is the two lists that we've created in values, and then sort them accordingly. And then we have our third bit where we now create a dummy head, which is a list with no data and a list with next, and then we call current dot head, and we call it to what? Sorry, we call current to head rather, which is a dummy head which we have here, and then we go through it recursively. Now, can someone I think the obviously the ingenious part, right? I say can someone as if I'm teaching the class, but what I'm trying to say that you will notice that the reason why we call current after calling head is one of the few things that actually stands out, because we are going to need this guy subsequently to locate the head again. And that's the thing with working with pointers. We have to be mindful of where we are coming from, and before pushing whatever our pointer is forward. Now we will see where we will use that, and it will make sense. Now we go through the values within the value list. So we call it recursion or a loop, right? And then we call current dot next. So current that will be the head at this point, and we'll create a new lead node and we'll point it to a value, to the value of the list, right? We'll see how this goes when we go through our debugger, and basically it will just take all the values within the listen and create a singly linked list, all the values within values, and create a singly linked list with them. And yeah, so we could also see some sort of some sort of illustration, right? A graphical illustration of what we're talking about. Now we have a dummy list, right? Before pushing the head, or before returning anything, we have sorry we have the so this will now be our return, right? Now, so that's exactly what it would be. I think this should be pointing this other way rather, if I'm not mistaken. You go agree. Not yet conversant with this tool, but I guess it is what it is. So okay, so we have our return pointing to this guy. So we have our return pointing to this guy, right? And this is where the head would now start, basically, because return dummy.next. This dummy, this is next, which is A. So basically that's why we still left dummy and created a current, right? So that's basically the illustration where you see where we have a list, and this dummy is initially pointing to 0, or it's pointing to none, and has a value of 0, and then we call our iteration and it creates A becomes the current, goes to B, and then points to next, is next to B, and then current dot next is B, and then we say current is equals to current dot next, right? And then we go to B, just the same thing, and over again until we complete creating the list. Now let's look at the see. So yeah, the print. Now we go into our print, and then we'll begin to see, we'll go through the first block and the second block. Now we will see that from the first block we've appended values, and the second block has also appended values, and sort has already also been called on it, right, to sort the list out. So now you could see values 1 2 3 4 5 6 7 8, where we had passed in 7 8 and 1 2 3 4 5. So basically you could see it here, right? And then we can then recursively go through the list as we begin to create our node. So you could see that current will be changing. When as value changes, current changes. As value changes over here, current also changes over here, because we are creating current nodes and obviously recursively going through it. So we create a new one and we continue in that fashion till we get done, and then our final result would be something like this, right? But obviously singly linked list, because that's what we are working with. So that's basically it for this one. Muchas gracias. Auf Wiedersehen. Choose. Okay, one more thing. Let's talk about the O of n. Now we have an O of n plus m here. We have an O of n plus sort here. And then over here as well, we have an O of n plus m, right? So now all these are on a list. And then we could see that the one that trumps them all is the sorting, which is O of n plus this. And for that reason, so that's the one we are going to be going off of, because that's the greatest recursion. So for time, that will be our recursion. And then for space, our main space usage was the values, which is an O of n plus m, right? So that's just it. Now, so that's how complexity is. Because if you're wondering, oh, why did we leave this guy and leave this guy and just choose this guy? So that's how complexity works. It just picks out the biggest value or the biggest recursion expense, and or not recursion expense, but basically the biggest expense or cost, and then that was what we hold as true for our O of or our time complexity. So that's it for this one. Muchas gracias. Auf Wiedersehen. Cheers.